All right, so welcome to the Akka Networks and Types talk. If you're over here, this also means that you're not in the Venkat talk next door, which is about Reactive Streams, which is something I worked on. So kind of assuming you know about Reactive Streams, we will touch something that is built on top of Reactive Streams in this talk, actually. So, who am I? Konrad Malawski, part of also GeeCON committee here. So kind of invited myself over here, but I do hope it's going to be interesting. Recently named the Java champion and located in Tokyo, Japan. All right, so hands up if anyone doesn't know what Akka is at all. So you know what Akka is. Do we have people using Akka? Hands up. Okay, and other people, have you tried it? Yes? Okay, so a fair mix of people. So, what does Akka really solve? So it's all about distributed programming. And yeah, we also deal well with concurrency on single nodes. That's really what actors are good for as well. And streams, for that matter. But really we think in terms of distributed systems, how we can make them easier, simpler, and at the same time high-performing. So before I dive into the actual topic of today's talk, which is the typed actors and a new abstraction that we have in Akka, which is the stream refs. Brief history, where it came from, and kind of to show you the road we already have taken and what the shape of that road has been in the last years or so. So Akka really started 2009. One of the first Akka talks, first few Akka talks by Jonas back then in 2010 was also at GeeCON actually, which is how I got introduced to it actually. And since then, in the Scala ecosystem, we kind of contributed the Akka futures implementation. They basically became the Scala futures. And then a number of other things came out of that. So we had circuit breakers already 2010. So nowadays everybody talks about circuit breakers. It's not really a new thing, because the moment you go asynchronous, you're going to need some circuit breaking. Okay, so we also have circuit breakers. Then the next step was, because previously futures and actors, this was all single node. But we said, hey, we want to do distributed computing, right? It was always the goal of Akka. So then the cluster arrived. So cluster brings you this location transparency that actors can talk to each other independently on where they're located, and they can even migrate semi-transparently, so you don't need to care about it. And we'll see why this is important, because this makes the trade-off we made in Akka with the untypedness of actors. It kind of explains it, because in a distributed setting, the typing and in a concurrent setting as well is not as trivial as just function calls, which is the reason why we had this any-to-unit signature for a very long time. Later on, of course, we included Spray, which became Akka HTTP. I worked on it quite a long time. So now we have cluster for all the internal communication. And remember this phrase, because actors is really within a service communication. And then we have HTTP to communicate with the rest of the planet, basically. Then we included persistence, so the actors can have persistent state, etc., etc. And CRDTs, again, extending the cluster. And finally, three or 4 years ago, well, 4 years ago we started on it, but 3 years ago became semi-stable, Akka Streams and the Reactive Streams initiative. So literally what is now being talked about in the room next door was initiated 3-4 years ago when I joined the Akka team, and we kind of started working on the Streams initiative. So then it arrived in JDK 9, which is why nowadays we have Java util concurrent flow interfaces. Okay, recent things we worked on, HTTP 2, again just improving the HTTP story. And here we have the typed woods, which is the topic of today's talk really. Then things on the side which are alpacas, or connectors for streams to various technologies. The artery, which is a new re-implementation of remoting, so something that sits underneath the cluster. And finally, a new thing that we're working on, and is shipped already, so multi-DC things, so multi-data center replication support and things like that. So as you can see, the theme here is becoming kind of more and more distributed, right? We started from simple concurrent systems, then clustering, distributed systems with HTTP connections, and now even multi-data center things. So this was a brief roadmap, but Module-wise, these are probably the most important ones, right? Actors, cluster, streams, persistence, etc. And the theme here is, which is the topic of today's talk, so networks and types, is that all of these in the last years have become typed. And most of them, for example, streams, always was type safe. Typed persistence, that's new. Akka HTTP was always fully type safe, so you cannot even return an invalid content type, for example, because it wouldn't even compile. You can't construct the wrong type there. So this argument that Akka is untyped is really more about the Akka actors, which, yes, correct, they, for the most part of the last years, have been untyped. And by untyped, you'll see what exactly I mean. But really, the theme of the last years has been all more type safety and more guarantees at compile time. And when I say that, I mean both Java and Scala APIs. We always have complete feature parity. So why do we need strict typing? Well, obviously, we want more compile time safety. And this is because in these distributed and concurrent systems, things get really fuzzy really fast because so many things talking to each other concurrently. So you want a bit more safety. But I would also argue that it is more productive to be in a more strictly typed system, also for understandability of such a code base. Let's say you have no idea about a code base, but if all of the methods and messages are strictly typed, then you can click through the thing and you figure out, okay, who is talking these messages or not. So to me, one of the biggest things about Akka typed is really the understandability improvements. To a lesser extent, that, someone sent an accidentally wrong message to an accidentally wrong actor. People sometimes say that this would be the biggest problem. In practice, it's not. I think the understandability improvements, this is the important bit here. So, and it's also kind of at odds with distributed computing. You have multiple versions of things coming up and down. Concurrently, maybe a thing was delivered or wasn't delivered, and we'll see how we solve that problem specifically. And it was also a topic of active research. This is only a few papers. The Akka project by Philip Wardler, and more recently one that more inspired us to do the current typed actors implementation is the Reactive Channels and Event Streams by Alexander Prokopec and Martin Odersky. So it's a relatively recent paper, and it certainly influenced the direction we took in the current implementation, although it's not directly implementing all of the concepts, and mostly because we try to make it pragmatic. Always in papers, it's sometimes a bit magical dreamland, and we try to think, okay, what would be useful in production in real systems? So we'll see how that worked out. Quick reminder what an actor is. So you have a mailbox, you insert messages to a mailbox, the actor will process these messages in order. And we handle all the concurrency around it for you. If you've never seen an actor, can I get my mouse here? Yeah, so the exclamation method, we read it as tell. And again, if you're new to Akka and Scala, sometimes people would say, Scala, they have so many operators. That is not true. We only have a question mark, the exclamation mark, and one special power user thing. So it's not overly complex API-wise, I would say. Okay, so you send messages, and in response to that, an actor can mutate state. For example, spawn a child actor to perform some task, or mutate some local variables, or send other messages to other actors, because the only way an actor can communicate is through messaging, and changes behavior. It's kind of related to state changes, but when we say change behavior, you can replace kind of the method, the function that will be invoked when you receive a message. Okay, reminder of untyped actors. So we have a sender. So inside your actor, you can say sender, and then you know, okay, this is where I have received this message from, and this is problematic. I'll explain why in a sec. Then we have, this problem that, messages can be any type. We don't have a way to restrict it at compile time. So you could theoretically send the wrong message. Again, I argue that's a lesser problem. It maybe looks scary, but in practice, not the biggest problem we have here. And then the receive method, which is the thing that will be invoked with the message once the message arrives at your actor, does not return anything. So it's completely side effecting, which kind of makes sense because actors that's what they do, they side effect, they mutate their local state. At the same time, we would like to be, return values are very useful, right? So let's improve that as well. So in 3 dots, how does Akka typed improve all of this? So Akka typed, or Akka typed actors, to be more specific. Oh no. Okay. So the sender is now part of the protocol. When I say protocol, I mean the message type that you're sending over. And why does it have to be like that? It's because the sender method is just a method on the class that you extend, and then it's impossible to change the type of the sender method depending on who sent you the message, right? Because that's static information, and someone sending you and having some type, that's runtime information. So we can't enforce random runtime things at compile time. So we made the sender part of the protocol, and it also solves a bunch of concurrency problems with, while you're just using actors, you're safe from all kinds of concurrency problems, but if you mix them with something else like a future, you could run into reaching for a sender, but it's the wrong sender because you're executing, I don't know, a minute from now in the future. So we address the sender problem, and we also address, the typing problem. So now an actorref, so an actorref is the object you get in your hands, and you can send messages to it. You never get an actor itself. It's hidden from you, kind of in the real object-oriented way. We hide the actual object you encapsulated, but we give you an actorref. And this is the type of the messages it can accept. Seemingly simple change, but took years to get right. Okay, behaviors now return new behaviors. And that's a new term. Previously we would talk about the receive method, etc. Now we talk about behaviors, and you could have used this style before, but it wasn't enforced, and it also wasn't, again, typed. So we'll see exactly what that means. So, reminder, classic Akka. We don't call it, I don't know, deprecated Akka or something, we call it classic. So, an untyped actor here have the problem cases we described. So the any kind of message can arrive here to unit. So this is the not returning any value problem. Unit in Scala is like void in Java. And here you have a pattern match. So you're checking kind of what message arrived. Here you have the sender method. So it's a method on the actor trait here. And this is the problem with the typing, that we couldn't type it correctly. Yeah, you can reply, of course, and that we don't return any value here. So it's just unit, right? So, enter typed actors. We're going to look at a mini example to see it a bit in action, and we can then later discuss how it expands to bigger use cases if you want. So, a burglar alarm, it can be enabled, disabled with the pin code, so it has multiple states. This will be the becoming a different behavior part of it. And it can accept notifications about some activity being someone opened the window, someone opened the door, etc. And when the alarm is armed, you would want to get some alarm notification about it, right? The door should not have been opened because you're not at home, right? Now, first importantly, and not unlike in normal actors, the biggest and most important part of designing a distributed system is really the protocol. And by protocol, here we mean just normal Scala case classes or normal Scala Java POJOs. And you'd model something like the protocol here, which is an alarm message, and it can be disable, enable, and then some activity. And the actor will be speaking this alarm message protocol. So this is our first look at these two styles of this DSL. So this is the more functional way. And first thing we can see, we're not extending a trait anymore. So it's more of a plain functions and composition style. And we can see that this enabled, with some pin code, it returns a behavior. So behavior really replaces what used to be the actor trait. So instead of extending an actor, you provide behaviors, and then you run these behaviors. So behaviors is what the receive method was previously, and now we have a first-class concept for them. This is very important because it allows us to have rich decorators with all kinds of behavior, just simply decorate another behavior, and you can compose them very nicely, which was, again, another thing people wanted to do with Akka actors very often. It wasn't that easy. So how do you build one? You say behaviors, it's a factory for all kinds of behaviors. You can say receive, which is the bridge to what we saw before in Akka Classic, and you receive a context, which in Akka untyped would have been just a method inside your actor, and a message. And you can also do receive message. You'd write receive message, and then you wouldn't get the context. So only the message, which is a bit briefer. The downside would be you would have to get the logger from somewhere, right? Sometimes that's fine. Maybe you're enclosing or closing over some logger. Maybe the class you're hosting this method in has a logger instance. Then that's fine. But here, we're using the built-in logger in the actor context. The upside is it's automatically provided with all kinds of, for example, metadata around, the actor's name and path. And also, if you're using some MDC information, it would also be included here. So now we just simply match on the message. It's exactly the same. And here, this is actually a return. So we're returning the new behavior here. So if we receive the disable alarm and the code is correct, then become disabled with the pin code. In other cases, we would either stay the same. Let me show you. So we stay the same behavior. This is an optimization, so you don't keep allocating the same behavior all the time. So you can do the behavior same. In other styles, you could also return the same object, but since you're in the middle of constructing it, kind of same feels nicer. Or you can ignore or drop messages. So now it's also explicit that you're ignoring a message. Now, most importantly, one thing that we changed here, and maybe you notice and maybe you don't yet, is because this is fully typed, this is not a partial function anymore. This is a total function, which means, the match here also can leverage the fact that it knows that what we're matching on has this type of alarm message, and if we forgot to match on some of the cases, the compiler would tell you, hey, you forgot to match on, what would it be? Enable alarm in this case. So here we do the underscore. So in all other cases, ignore the message because it's not part of this state. In previous Akka, you wouldn't get this warning because, the type is any, so it could be anything. Here you would get warnings. So last line in a given handling is becoming this new behavior. And then if you want to enable the alarm, again, if the code is correct, you become the other behavior again. So it's this mini state machine, which we found is a very useful way of modeling actors. Sometimes people in normal Akka would do a mix of those two styles. They would do this becoming between states and some local state, which kind of affects the state as well, right? Now we kind of encourage this style. You can, of course, keep closing over values and having them, but this is kind of one recommended way to handle this. And we'll see how to do another style if you really will have a lot of state, for example. So compile time safety, how does it actually appear? Also one thing here, now the top actor in your actor hierarchy. So when you have actors, they form a hierarchy. And in Akka Classic, the top actor was a built-in in Akka, and you could maybe configure what it should be doing. Now in typed, we decided that, it's your actor system, and you're in charge of what it should be doing. So the top actor is kind of a user guardian, how we call it. And when you start the system, you give it some behavior right away. Does this mean that you should have one actor system per actor? Absolutely not. An actor system is a heavy resource. It has all kinds of thread pools, etc. But it also means that this top-level actor becomes the one place where you can start all the other actors and you can more understandably start your system. Because previously you could start top-level actors anywhere you have an actor system. So randomly from the side somewhere. Now it's you know where you're starting, you know which the top level actor is, and again, it's a more guided way to build the system. And the other upside we talked about here is if you were to send a completely random message, it wouldn't compile, right? It wouldn't compile telling something that, hey, yeah, got string but expected, was it alarm protocol? I forgot the top level type, but you got the idea. So that's local and that's fine and easy, but the really powerful part about actors is that the same abstraction, so exactly the same way of communicating between actors, works in a distributed setting as well. Exactly the same thing. You don't need to do anything special. So let's see how this works in an Akka cluster. So a cluster, and sometimes people get confused and think it's a very heavy thing or something like that. I would actually argue it's probably the most lightweight clustering thing you can find out there, because it really is just a membership. So the nodes know who else is part of the cluster, and a little bit of heart beating, right? But we also do it sparingly with a pandemic algorithm there. Now, in Akka Classic, we did have some form of locating actors by names, but for one thing, it would be simply discouraged. You'd be rather encouraged to pass references around, because you could make a mistake, and I don't know, if you locate actors just by a name and you make a typo in the name or someone renames something, that's kind of error prone. So now we introduce something built in, and the actor system has something that's called a receptionist, and let's see how that works in action. So it's something that will allow us to do service discovery, but specifically for actors. And the reason we're going to do it specifically for actors is because we want to also make sure that the type of the actor ref I want to talk to is correct. So when we register with the receptionist, it will also know, okay, this actor is handling this and this type. And we could do some error logging if you do the wrong thing. Okay, so again, the distributed version of it. So you can have any number of nodes, and a sensor can report activity from the alarm. Okay, so the receptionist, this is the registering yourself with the receptionist part. So kind of like checking into a hotel. So you get the receptionist, and when you start, now we have a behavior. This is what I said with the composing behaviors thing. So it's still just a behavior of the alarm message, but actually, before it starts, it will execute this code. So it's like a pre-start, if you know Akka Classic. So before you start the actor, do something. Previously, we would have special callbacks for it, which would kind of mix things, because some things are callbacks, some things are messages, and there's two styles to do things. Now everything is behaviors. So we do a setup, and when we start this actor, we register ourselves with the receptionist. And we use some shared key. So that's the name. But this name, again, is typed, and you have the type there, and we can keep that information as well. So, and then we become enabled, right? That's easy. So, this is just a new protocol about window opened. Now we can see when someone else starts, the sensor starts, it will get the receptionist, and it will ask for, hey, receptionist, subscribe myself to this alarm key, and this is the reference. It should send these notifications about new alarms appearing in the system. So when a new alarm appears in the receptionist, it will notify everybody who's subscribed to it, like a pops up, but specifically for typed service keys. And then we simply return the behavior that actually implements the logic. Now, one other thing here is that I kind of cheated here, and I'm like, yeah, but the typing dance would be a bit too much. And there's ways to make it, well, purely typed. But this time around, I think this is much easier. So we can say, okay, if I get a listing, I insert to my list of alarms the new alarms, and if I get a window opened, I notify all the alarms to do the thing. But from the outside world, I don't need to tell anyone that I'm using, this nasty any here. So I do an arrow, which again brings me back to kind of happy land, the type I want to expose to the outside world, even if I did something kind of nasty inside. The way to do this properly would be adapters, but for this simple use case I decided let's show how to make it as simple as possible, also for fitting on slides. So, immutable behavior is basically like Akka Classic, where you have a class that you extend, and we call it a mutable one because it has some variables. So here we have the alarms, and the name kind of implies, yeah, you will be mutating the state here, kind of like we did in previous style actors. And instead of the receive method, now we use a onMessage, and you get a message, but the contract is the same. You're kind of asked to return a new behavior, which, because we're in a class, we can always return this. You could also return behaviors the same, would be the exact same thing, and also optimized the same way. So I would actually recommend this style if you have an existing code base and you want to migrate and get all of the benefits of being in a typed system, and you don't want to go into the fully functional, etc., because migrating from Akka Classic to this style is almost mechanical. You change what you extend, you change the receive method to onMessage, and you're kind of done, and you got the static typing guarantees. So keep that in mind in case you're migrating some code. And how to run such a system? Literally, it's you can start multiple actor systems in one node. It's kind of silly, but you can. And we simply join them into a cluster. And this is all you have to do. You have a running cluster already. In practice, this would be, of course, multiple JVMs on multiple nodes, and you'd use a discovery mechanism to discover them. We also have some automatic discovery mechanisms. If you're interested in that, Google for Akka Cluster Bootstrap, and we have a number of implementations that uses, I don't know, Kubernetes APIs, AWS APIs, or DNS to discover neighbors and form the cluster. So, all right. So this was the actors part, which kind of adds the typing to the networky parts. And now let's take the opposite. So something that was typed, was even back-pressured, but wasn't networked. So Akka Streams and Reactive Streams, by that extension, are very cool and nice, but it is not a network protocol. It never was intended to be, at least not Reactive Streams itself. We did want to and still want to, and there exists some attempts to make it a network protocol. So RSocket, for example, is one attempt at that, or Streamrefs that I'm going to show in a few slides. So we had actors which are distributed but not typed, and now let's look at streams which are typed, weren't distributed, and let's make them distributed. And I hope I have a disclaimer there, but if not, we'll see. So, quick reminder, Reactive Streams. Does anyone know Reactive Streams? If you know Reactive Streams, hands up. If you don't know Reactive Streams, hands up. Okay, just checking if you're awake or not. So literally, Reactive Streams, what now is called a Java util concurrent flow, literally it can be explained in this one slide. It is not at all easy to implement, but the general idea is that you control the rate of sending messages through a system such that a downstream, so the slow side here, the blue side, is never overwhelmed with messages. Why do we do that? Because otherwise you'd get out of memory, or you would have to drop messages and resend them, etc. So we have that, and this works, exists, etc. And it had two purposes, really. So one was avoid unbounded buffering, which is kind of why we do the flow control. And the secondary goal, which is why it ended up in the JDK, is that it's an interrupt interface. So if you go to some talk and someone tells you to extend publisher, tell them he's wrong. He or she is wrong. Because it's really intended to not have to implement them directly, but use things which underneath use Reactive Streams. Okay? So why is it hard to implement if it's just 4 or 5 methods? There's a lot of meaning and semantics around when you're allowed to invoke which method in Reactive Streams. So that's a set of rules. So you should be using Akka Streams or any other implementation. I don't know, RxJava also implements Reactive Streams. You could be using that. So this is how you run it in like a 20-second pitch. We have abstractions that we call flow sync source. And we made the conscious decision to express in the type system that something is only emitting data, only receiving data, or a processor of data. It's also directly a one-to-one mapping to Reactive Streams. So a publisher is a Reactive Streams publisher is a source, a Reactive Streams subscriber is a sink, and a flow here is a processor in Reactive Streams land. So in case you know the Reactive Streams terminology, now you know the corresponding Akka Streams verbs. And now, what Akka Streams provides is, well, it implements the protocol for one thing, but it also implements all kinds of operations, right? Because just Reactive Streams, you can't even map over it. You can only send messages. You can't do any operation on it by itself. So we implement all kinds of, back pressure timeout, what else? Interop with Java collections, interop with Java streams, interop with literally every database on the planet, which is the Alpaca project. Okay, so Alpaca is this collection of connecting to stuff. And this is about, I said that we don't do Reactive Streams over network because it's not a network thing, while at the same time, interop with all these things and more. I don't know, let's pick one. What's an interesting one? What would be good? First is boring. Let's do TCP. Okay, so TCP has flow control built in as part of a protocol, and I just said Reactive Streams doesn't do network. Well, if you do Reactive Streams to a socket, like a TCP socket, and the socket will be telling you, yeah, I couldn't write to the network, so we in Akka can translate this information to Reactive Streams back pressure, and this has always worked. This is how Akka HTTP works. This is how Reactor works, and all these libraries. And that is different. So understanding a back pressure signal from, I don't know, from Cassandra, which says, yeah, I can't write anymore because I'm busy doing other writes, is different than emitting elements over the network using the Reactive Stream semantics. Not sure if that's super clear, but we'll get to it, hopefully very soon. So, brief summary, I had to include this picture because I was kind of really laughing about it. So don't build your own flow implementations. It's kind of hard, especially if you're, connecting random stuff. And if your answer is, oh, but there's no connector for the system, I need to connect, well, then build on top of Akka Streams, build on top of Alpaca, use something like that. And please don't be like, but I really want to implement my own flow implementations. Please don't, but if you're really wanting to, you could, but then at least please do use the TCK. So it's a set of tests and compatibility rules. So if you really want to implement something from the ground up, you can, but at least please use the TCK. Anyway, so we kind of tackled, we have some way of talking over network with things, but it's not the same as just two things on both sides and emitting elements. So it's kind of different. So now let's talk about what I kind of pitched a second ago. So Akka Streams and Reactive Streams over network. So it's going to be that both sides are in Reactive Stream, and we want to connect it, kind of distributing the Reactive Stream there. So the brief pitch is that streamrefs, how we call this feature, is Reactive Stream semantics over network boundaries. So both sides are Reactive Streams, Akka Streams. And also if you know actors, then it's pretty much like an actor ref where you can send messages to, but for streams. So it's lightweight and simple, and that's the disclaimer I wanted to show. It is not a Spark replacement by any means. It's more like a very convenient way to send messages in a back-pressured way between two or more systems. It's not a Spark. It's not a Hadoop, etc. You could build one of these using these abstractions, but by itself, it's not it. So, what do we want to change here? So this is life without streamrefs. You're doing some HTTP requests to some other node, and this other node gets overwhelmed because, well, the left system is a bit faster, the right system is a bit slower, and it gets overwhelmed, and eventually it will start either sending some 500 responses or not responding at all. And we want to solve that, and not by just slapping circuit breakers on it. As I said, we had circuit breakers for many years, and it's good for handling failure, but it is not good for flow control, right? It's like running your car into a wall and then figuring out that probably was a bad idea, and getting a new car and doing it again, right? You don't want to keep driving a car into a wall. You want to keep the car on the road. So this is stream refs. So stream refs allow you to, by changing very little code, connect these two systems in a flow-controlled fashion. And then the rate of the messages being sent will be evened out and appropriate to the speed of the downstream consumer. So this is the kind of funny picture about it, but a more visual picture would be like this. So you have some source of data, you're doing some transformations, so that is in flows, and then you use this special sync, which returns, when you run it, it gives you a source ref, because you're kind of referring to the source, right? And then the source ref you can give to someone, well, this other JVM, so you can give it using extra messaging or anything else really, and you can give someone the source ref, and they can connect other operations to it, operations they want to run on this other JVM that's distributing the stream part, and then they run it. So what happens is, so some transformations will be happening on the local side, then you go into the source ref, and the rest is being sent over the wire, and the rest of the transformations can happen on the other side. And again, the sync, the other side, controls the rate of this processing. So we have the origin side, and let's see how this is constructed once again, with more arrows and explanation maybe. So this is literal Akka Streams code you would run with stream refs, and you want to get a source ref, right? This returns to you a source ref, which is this representation of the handler to this running stream. Then you can hand it over to the other system, and they can get the source and run it. Okay? And then underneath they get connected and the data starts flowing. We can also do the opposite. So this is when you have the data and you want to offer someone to consume the data, but you can also do the inverse, kind of like passive mode in FTP, where you have the capability of accepting data, and you want to offer someone, hey, I'm ready to accept data. And this is very interesting if you have some system that, I don't know, like a file upload system, maybe a bad example. Some system that has some kind of rate or limits about how much it wants to be receiving data from many customers. And then you can basically think about how many you want to run concurrently and only hand out that many sync refs. So we hand out a sync ref. So here is the opposite. We have stream refs sync ref, and you run it with some sync. So this is could be a file sync, could be a database sync, could be a JMS or Kafka sync, anything really, which is where the Alpaca things fit in. So all of these gray boxes, well, except for sync ref, but like a sync and a source, this could be any Alpaca connector, right? So anything, any write you can suddenly distribute across your system. And then we hand it over, and the remote side can use any source. Again, could be database, could be file, could be WebSocket, could be incoming HTTP connection, because we model everything as Akka Streams. And they can run it into a sync, and the data will be flowing again, no faster than the sync ref allows. Let's look at actual code. It's probably a bit small. So let's zoom in a bit. Actually, this example is in Java here. So you have stream logs. You see this is a source of string. The second parameter, we're not using it here. But this would be, it kind of is, when you do the run with, this is where the source ref appears from. So the logs don't materialize any value. This is why we say not used. But it's a source of strings. So when you do logs, run with, stream ref, source ref, you get the materialized value, which is the completion stage, because it's asynchronous, of the source ref. And then you can send it over to the other side, which we do here. So it's the pipe of the logs offer to the sender. A bit Java verboseness, but not too bad. So the same in Scala. A bit less code. So you have a future, and then we say map, and we just reply pipe to sender. Slight niceties and DSL there, but basically the same concept. And then the receiving end, what they would do is they receive in their actor, for example, you would receive Should I show the Java code or Scala code? Java, Scala, Scala. Okay, so you get the offer, you get the source ref, and you run into a kind of boring sync, which is just a print line. But you get the concept. So here we kind of bridged the other way around. And the most important thing is, I think, marrying both words. Now we have typed actors, we have typed distributed streams, and everything kind of fits together, which is the big kind of feature of all of this. So in other news, as I'm kind of approaching the end of the talk, and we will have some other minutes so you can ask random questions about it, what else is coming? Because the subtitle was also kind of future of Akka. So we also have a new transport. So the transport is what actors use to send the messages. We even recently did, so one of them is using Aaron, a very high performance, etc., but using UDP, which sometimes isn't that suitable for some organizations. And also we couldn't do encryption on it. So there is datagram TLS, but it's kind of slow, which would defeat the purpose. So now we have also archery, which is when you're remoting, on TCP with TLS if you need security on the transport layer. We have a multi-DC feature and typed persistence. So if you used Akka persistence for event sourcing, we have it also in a typed API. Why would you care about this remoting? Because the classic remoting actually is not that highly performant. It's like, yeah, okay, reasonable. But literally the new remoting implementations are a 10x improvement, and you get that 10x improvement by literally just enabling it. So that's probably pretty good if you need throughput. So also, this is just a random fact I wanted to insert, because we kind of talked much about the types, right? Both of the APIs were types. But what is actually on the network when you do an actor message? Has anyone seen an actor message, how it looks, what the bytes are, what it contains? So let's have a look. This is an actor message. And if you see the actual payload, you can shout it out. What's the payload? What's the message? What did I send there? Yes, it's the last 5 bytes. Here, it's just this hello. And all of the rest is just, they want to say crap, it's needed crap, because it's the address of the sender and the address of the receiver and the metadata about the type of the message that is being sent. But you can see it's kind of dominating the message, especially for small messages. For bigger messages, doesn't matter, but if you send really small messages, it's a bit of a waste. So now we also do compression. So we have a algorithm that the nodes communicate and exchange kind of keys for often used values. So if an actor is very often communicating, it would be compressed into a single integer, and now all the dots are carrying the same information that previously was directly transferred as strings. But it's all the same information. Smaller payload means better performance. And now you know how an actor message looks like as well. Yeah, we have multi-data center, and recently we launched a Discuss forum. So if you know about the Akka user mailing list, we're now moving to the Discuss forum, so it's Discuss Akka.io. You can go there and ask any kinds of questions. Do check out the blog. We try to not only do announcements, but also more like fun write-ups, how to do stuff with Akka, instead of just dry documentation, which is the documentation. And this is a pre-announcement. I've been tweeting about it, but wasn't quite public yet, and really maybe shouldn't be yet, but whatever. There's going to be a new Coursera course. I'm working on it recently. If you know previously the Martin Odersky course about Scala and functional programming. So exactly that same thing, but about building reactive systems. So it's going to be Martin Odersky doing an introduction about functional things, then Roland Kuhn about typed actors, and me talking about Akka Streams. So if you're curious, want to learn, and then also use this kind of Coursera always forced me to actually participate and do the exercises, right? So it's a good way to learn, at least for me. So it should be out in a few months. So have a look out for it. So thanks for listening. If you have any questions, I'd be more than happy to show code or talk about anything you might want to know. And I do have stickers for good questions versus special sticker. So any questions? One over there. Thank you.
So the new typed actors API that G showed, right?
Mm-hmm.
How stable is that? Because that tended to change a lot in the past.
Yeah, you're right. It has been changing very aggressively over the last years because we weren't happy with what it was all the time, and now we actually are. So the API, well, technically it's still in may change state, but the actors themselves, this will not change. You can pretty much use it and assume this will not change. What will change in Akka typed? Slightly, probably not very much, but the persistence API in Akka typed may change a little bit. Cluster APIs will not change anymore because we're literally migrating the entire ecosystem. So if you want to use Akka typed, you have everything in Akka typed. You don't have to do a weird interop. Although interop works. If you have something then untyped, or you like untyped for some reason, or don't want to rewrite some part of the system, and you have some new part of the system in typed, they interoperate very nicely. But you're not forced to do a big bang migration. You can do a step-by-step migration. Anyone else? They're in the back.
Hi.
Hey.
So, have you seen the talk by John DeGoes from the Scholar conference? Yeah. And what are your thoughts about that?
I don't think it had much substance.
There were some snippets comparing the solutions in Akka and in Scala Z.
I mean, comparing to kind of ignoring 4 years of our work. I felt like he picked specific old things which we've been exactly addressing over the last 4 years. So,
right. So people in the conference and in the hallways were very happy with this kind of talk. So my second question is, what do you think about that?
I don't understand what you're saying.
So many people think that Akka is very old, and this new Scala Z is very, very nicely marketed by some people, including John, right?
Well,
and people from Leibniz, like yourself, are not discussing it officially and in public. So
well, I don't feel threatened by it. That's kind of.
Sorry?
I don't feel really threatened. It's addressing different needs, and I don't think many of the points made in that talk are up to date. So why would I go out and start a discussion where I don't think he will ever agree to anything I say, right?
Okay, yeah, fair enough. Thanks.
Yeah, thank you. We have like 2 more minutes. So think of good questions, good stickers. Limited edition, only 10 on the planet.
A small comment about this talk on Scala. Scala Z, it's not yet released, so this is my comment. And my question is, Akka Streams over the network, is it production ready?
That's I kind of screwed up a bit. When I was testing it, let's put it this way, the currently released version has a bug. It is fixed in master. You would have to disable a timeout, so the timeout would trigger anyway, even though there's things going on. So there is an existing bug in 2.5.12. It's fixed. It will be fixed in 2.5.13. Otherwise, it's ready. Yeah.
And some examples where can I use it in real life?
So this was actually developed for a friend of mine at a customer, a really big customer, and their use case was twofold. There is one use case which is sending a lot of small messages. Let's say you have a sensor. It's like a sensor thing. So they have a lot of sensors, and we have this thing that ingests all the sensor messages, but it doesn't have to ingest all of them. So actually the sensors are smart. They're smart devices. They can conflate multiple measurements into a bigger measurement, just average the thing, and then send one. And with streamrefs, this is literally 2 lines of code to implement that feature. Because if a server doesn't give demand, the downstream servers collapse the messages and they send over one update instead of 100. So it literally made the load on the server side much, much smaller. So that's one use case, and this already works with this. And the second use case they had was, it's not really files, it's huge messages, because they really like actors and they want to use the convenience of it. But the messages were big enough that it clogs the pipe, so to say. And what we can do with Streamrefs, and that's not implemented yet, but have a dedicated connection for the big things, and then do like a global throttling around how many big things can be sent at the same time. So it's a replacement for having to manually do file uploads and stuff. So that's the two main use cases. It also replaces the work pooling pattern. If you know work pooling, that basically deprecates the work pooling pattern. You don't need to implement it manually anymore. And last question, maybe.
Okay, so my question is about the network as well.
A bit lower.
The network as well.
Yeah.
So do you have any comment about the delivery guarantees? How that works?
Yeah. So this rides on actor messaging. So the delivery guarantees are the same as in actor messaging. And for example, sometimes people are confused about us moving to UDP, right? Well, it's not just UDP. It's Aaron UDP, which has the same delivery guarantees as TCP. And the only case where we would lose a message is if the connection gets forcefully and utterly destroyed and we can't recover it. Then you'd get a message loss. But in Streamrefs, you would not get a missing element. What you would get is, so we buffer and sequence things. So if this would happen, in practice doesn't really happen that often, you'd get a stream truncation event where the thing would be truncated. So you can assume that no gaps, and in sequence, you cannot assume a magical redelivery. That's another feature that would be nice for Streamrefs to have redelivery in it, which would slow it down, but we could make it like an option or something. Okay, last one.
Yeah, I'm just hoping for the best question, smartest or stupidest. So if I guess it was a lot of effort to do it. So now, if Akka is type safe, will you change the company name back?
Would love to, but yeah, probably not. I would love to. Well, our package names are still type safe, so Okay, thank you very much. If you have any other questions, let me know. Thanks.